future from.
Okay. Let's go ahead and start with what you guys got from the video. Okay. So there's two types of carbon. What are the two types of carbon it talked about?
Carbon 12.
Carbon 12 and what?
Carbon 14.
Carbon 14. But does carbon 14 happen naturally?
No.
How does it turn into carbon 14?
Nitrogen.
Yeah, what happens to nitrogen?
Way.
It gets hit by the, let's just go to the sun. We'll keep it nice and simple. So nitrogen gets hit by carbon, or gets hit by the sun and turns into carbon 14, okay? How do plants and animals get carbon?
They eat plants.
Okay, so we have our plants, and our plants absorb carbon, so we have carbon 12 and carbon 14, just all in the plant. And so how does an animal eat? An animal gets it by eating it. How does a carnivore get it?
Eating the animal.
Eating the animal. Right? Okay. So do you think carnivores and herbivores are going to start with the same amount of carbon? No, they don't, right? And this is why carbon 12 is going to matter as well. Because carbon 12 is going to be a baseline to let us know what type of animal it is. We're going to use it as a comparative to see the levels of carbon 14 versus the levels of carbon 12. If there's a ton of carbon 12, we're going to have a better idea of, is it a carnivore or an herbivore? We even noted the point that in humans, that if you are a fishing society, there's a lot of carbon in fish, you're going to have higher levels of carbon. And so we know based off of different cultures what type of levels of carbon they have. So when we go to start looking at the fossil past, we can get an idea of what type of communities they have and what type of resources they ate. So this is, once an animal dies, will it get any more carbon?
No.
Hopefully not, right? So animal's dead, and it gets no more carbon. So the whole thing that we're going to do with this is we're going to measure the starting point of how much carbon 12 it has, and we're going to look at the amount of carbon 14. What's going to happen to carbon 14? Did you guys pick it up?
Decay.
It's going to decay, yes, and you guys used half-life. That's a really good term. So with half-life, did anybody pick up how long the half-life was?
5,000.
5,730 years. So let's just say in our imaginary animal that it dies with 100 carbon 14s in it. We're just going to do it that way because it's nice and clean. So we're going to look and we're going to graph it out. This is the amount of carbon 14 it has. And let's say it starts with 100. This is the amount of time that has gone by since it's died. Okay? You guys brought up half-life. What decay means is, in my head, I think about it, and it's like shaking and just wants to turn back into nitrogen. So once the animal dies, that carbon 14 is going to eventually decay back to its original state and turn back into nitrogen, okay? And you guys brought up the half-life. So what scientists have been able to measure is that every 5,730 years, approximately half of the nitrogen that is, or the carbon 14 that is in the remains will decay and turn back into nitrogen. So if we started with 100, what, after 5,730 years have gone by, how much carbon 14 would we assume? 50. Now, what happens if another 5,730 years go by? How much would we assume? 25. And it's really important that you recognize that too. It's not half of the original amount. It's half of what is left, okay? And so we would assume there'd be 25. And this is going to go on and on until we are no longer able to detect that there's any carbon 14 in the fossil remains. How long did anybody pick to see how? About 50 to 60,000 years. So if something is within 50 to 60,000 years, we're able to date it and have an accurate description. So this is the activity you guys are going to do. What you guys are going to do is you guys are going to come across this dead body of an M&M, okay? What are the chances that you get M's up versus M's down? 50-50. So let's say approximately you start with 100, and you take them and you shake them and you dump them. What are the chances that 50 or like the probability is that how many will be M's up and M's down? 50-50. This is going to represent your half-life. So what you're going to do is you're going to have one piece of paper with everyone's name on it. You're going to have a graph, do it long ways. I'm going to give you M&Ms and you're going to count them. You're going to take those M&Ms and that's going to be your starting dead body count. That's what your carbon 14s are starting at. You're going to then shake them and dump them out. All the M downs have decayed. What did those turn into?
Nitrogen.
They turned back into nitrogen. You are then going to count your M's up. Your M's up are still carbon-14s. You're gonna count them and then plot them. And then you're gonna, how many years have gone by for that first plot? 5,730. Then you're gonna do it again. And you're gonna count with your, only the carbon-14s. All your M's down are gonna decay. You're gonna take them out. You're gonna plot it again. What happened, and you're gonna do this until you have no more carbon-14s. What happens if you have one M&M, and you do it, and it's M up? What do?
Keep going.
You keep going. But how many years go by? 5,730. What if you shake it again, and it's M's up again? What do?
Another 5.
You keep going until it decays, it goes away, okay? Couple things I want to give you advice on. Do not make your graph like 150, 25. Well, that was that was too small. 150 and 25, because your graph will look like this, and this is a different relationship. Your graph should end up looking like this. 50 should be in the half point of 100. Do you guys get what I'm saying? Here, 25 is in the half point of 100. It's not, I just don't, a lot of times students do that. Don't graph it that way. This is a completely different correlation, and I won't get into why that matters. Okay, and then when we're done, we're going to look at the graph, and we're going to make we're going to be able to answer some questions about the graphs that you guys made. All right. They take a literal sample of the bones, and they destroy it, and they do like a mass spectrometer, and they look at what chemicals are found in the bones.
That's what was confusing.
I'm actually really good at pouring like about 100. I'm not joking. I've done this a lot. Everyone understand what's happening?
Yes.
Guys, I know we have one group still kind of finishing up. There's a couple things I want you guys to think about when it comes to this. For one, did everyone start with the same amount of M&Ms?
No.
No, which makes sense. Not every animal is going to start around the same carbon. For two, I want you to also think about the fact that we're not just dating those dates, those half-lives. Those half-lives are guiding, so we can date all in between it. So think about it. If I asked you right now, guys, look at your graph and tell me how long has passed with 36 carbon-14s. Can you tell me? You could look at your graph right now. Go on the side. Where would 36 go? Go. You guys get how to use it, right? Does it get what I'm saying? It's really important that you know that as well. So guys, look at your graph. How many years have gone by if you had 36 carbon-14s?
Approximately 11,000.
We have 11,000 over here, okay? So 11,000. How long for somebody else? 9,000. Okay, so this is a really good, let's stick with those two dates because they work really well. So if you have 11,000 and 9,000, that's about how much time has passed, right? So you're digging, you go, you see, and there's 34 carbon M&Ms, whatever you want to call them, carbon-14s. Well, you guys have two different dates, which is actually really good. And this is something I want you to think about. This is why we always have a date range, because it's not going to be identical and exact for each individual. We do know that if you have 36 carbon-14s, it's not going to be 2 years have passed, or 2,000 years, and it's not going to be that 40,000 years have passed. We get a date range. We can sit there from what our math for this example is saying, hey, 36 carbon-14s, those remains have been around for 9 to 11,000 years. This is why you always get the approximation. This is why you get a date frame. We're never going to dig and be like, that died 3,221 years ago. No, we don't know that, right? We can look at it. We can look at the remains like, okay, these are the dates that it's going to fall into. And so why you're always going to get a date range is because of this. Does this make sense, guys? Okay, what happens if you find the remains and there's no carbon-14 in it? What can you say?
Over 60,000.
It's older than 50 to 60,000 years old. You're able to then go, okay, we can't date it. Then what you do is you go and you find a different isotope that has a longer decay rate, and you look at something else. Radiocarbon dating is pretty cheap. Most of our fossils are, oftentimes in that time frame because it's really hard to fossilize, and we're going to talk all about that during this chapter. Okay, so I want you guys to go ahead and turn in your graphs with everyone's name on it, and you guys will get points. Please hit the M&Ms. All right.